with some remarks on boilers, bats and Chinese junks. That the ship went faster through the water, and held a better wind, was certain, but just before we arrived at the point, the gale increased in force. "If anything starts, we are lost, sir," observed the first lieutenant again. "I am perfectly aware of it," replied the captain, in a calm tone, "but, as I said before, and you must now be aware, it is our only chance. The consequences of any carelessness or neglect in the fitting and securing of the rigging will be felt now, and this danger, if we escape it, ought to remind us how much we have to answer for, if we neglect our duty." Captain Marryat, Peter Simple. The easiest structures to think about are generally those which have to resist only tensile forces. Forces which pull rather than push, and, of these, the simplest of all are those which have to resist only a single pull, in other words unidirectional tension, the basic case of a rope or a rod. Although simple unidirectional tension is sometimes to be seen in plants, especially in their roots, the muscles and tendons of animals provide better biological examples, and so do vocal cords and spiders' webs. Muscle is a soft tissue which, when it receives an appropriate nerve signal, is able to shorten itself and so produce tensile forces by pulling in an active way. However, although muscle is a more efficient device than any artificial engine for converting chemical energy into mechanical work, it is not very strong. So, to produce and sustain any considerable mechanical pull, muscles have to be thick and bulky. Partly for this reason muscles are often attached to the bones which they have to manipulate by means of an intervening cord-like tension member made of tendon. Although tendon is unable to contract itself, it is very many times as strong as muscle and therefore needs only a small fraction of the cross-section to take a given pull. Thus the function of tendon is partly that of a rope or wire, although it can also act as a spring, as we saw in the last chapter. Although some tendons are quite short, many of those in our arms and legs are very long indeed, and they run through the body in almost as complicated a way as the wires of an old-fashioned Victorian bell system. As far as our legs are concerned, muscle is not only bulky but heavy, and the object seems to be to arrange for the center of gravity of our legs to be as high up in the body as possible. The reason for this is that, in normal walking, the leg operates as a pendulum swinging freely in its own natural period and therefore consuming as little energy as may be. It is because we have to force our legs to oscillate faster than their natural frequency that running is so tiring. The natural period of swing of our legs will be faster the nearer the center of gravity of the limb is to the quite a long way away, high up in our arms. So the hand is enabled to have much more slender proportions than would be the case if it had to contain all its own muscles. The advantage of this arrangement mechanically and perhaps aesthetically is obvious. In artificial structures there are a number of simple examples of unidirectional tension, such as fishing lines and loads hanging from cranes. These differ very little from the problem of the brick and the string which we discussed in Chapter 3. However, many of the more interesting cases, such as the rigging of a ship or the design of aerial cableways, are apt to be beset by uncertainties and complications. In the rigging of a ship there would, of course, be no difficulty about determining a safe thickness for each rope, provided only that one knew what loads they would have to carry. The difficulty lies in predicting the magnitudes of the many different forces which operate in so complicated an affair as a sailing ship. Although there are several ways in which one might set about this, I strongly suspect that most yacht designers prefer to rely on what might be described as experienced guesswork. However, it is just as well to get one's guesses right, since the failure of a vital piece of rigging is likely to result in the loss of a mast. If this happens when the ship is caught on a dangerous lee shore, like Marryat's frigate, then the consequences will be serious. Nowadays skiing is a vast international industry which is dependent upon the reliability of many thousands of cable cars and ski lifts. I suppose that most of us have worried, in our more vertiginous moments, about the strength of the wire ropes which support chair lifts and cable cars above what seem to be rather frightening chasms. Actually, accidents very seldom occur directly from the failure of one of these cables in tension. This is because in this case the static loads are known pretty accurately, and it is not difficult to do the sums and ensure an ample factor of safety. More serious risks arise from such matters as the excessive swaying of the cables in the wind, so that the cars are likely to strike each other as they pass or perhaps to hit the supporting pylons. Here again, designers seem to rely mainly on precedent and guesswork. A very different application of unidirectional tension theory is concerned with the strings of musical instruments. The frequency of the note given out by a stretched string depends, not only on its length, but also upon the tensile stress in it. In stringed instruments the appropriate stresses are produced by stretching the strings which are made of stiff material, such as steel wire or catgut, across a suitable framework, which may be the wooden body of a violin or the cast iron frame of a piano. Since both the strings and the framework are stiff, very small extensions greatly affect the stress in a string and therefore the frequency of its note. This is why such instruments are so sensitive to tuning. It is also why one can use the note emitted by a rope when it is twanged as an indication of the stress in the material. The Roman army used to require that the officers in charge of military catapults should have a good musical ear, so that they could assess the tensions in the tendon ropes of these weapons when they were set up and tuned for action. Although the human voice differs in many ways from a stringed instrument, somewhat similar considerations apply to it. The mechanisms of voice production are rather complicated, but our larynx plays an important part in both singing and talking. It may be interesting to note that the various tissues of the larynx are among the few soft tissues in the body which can form approximately. In order to cause the necessary stresses, they are, in fact, stretched by a good 50% or when we want to achieve the top notes. Incidentally, the higher frequencies of the voices of women and children are caused, not by higher tensions in their vocal cords, but simply by the fact that the larynx is smaller and the vocal cords therefore shorter. There is a surprising difference in this respect between grown-up men and women, the relevant larynx measurements being about 36 mm for men against about 26 for women. However, the larynxes of both boys and girls are of very similar size up to the age of puberty. The breaking of boys' voices is due, not to any change of tension in the cords, but to a rather sudden enlargement of the larynx around the age of 14. Plants and animals might be regarded to a considerable extent as so many systems of tubes and bladders whose function is to contain and to distribute various liquids and gases. Although the pressures in biological systems are not usually very high, they are by no means negligible, and living vessels and membranes do burst from time to time, often with fatal results. In technology, the provision of reliable pressure vessels is a fairly modern achievement, and we seldom stop to think how we should get on without using pipes. For the lack of pipes capable of conveying liquids under pressure, the Romans incurred enormous expenses in building masonry aqueducts upon tall arches in order to carry water in open channels across miles of undulating country. The earliest approximations to pressure-tight containers were the barrels of guns, and, historically, these were never very satisfactory and quite frequently failed. A list of the people who have been killed by the accidental bursting of guns, from King James II of Scotland downwards, would be long and impressive. Nevertheless, when gas lighting began to be installed in London, soon after 1800, the pipes had to be made by Birmingham gunsmiths, and in fact the earliest gas pipes were actually made by welding musket barrels end to end. Although there are innumerable accounts of the history of the steam engine, relatively little has been written about the development of the pipes and boilers on which it depended and which, in reality, presented more difficult problems than the actual mechanism. The earliest engines were very heavy and bulky and consumed vast amounts of fuel, chiefly because they worked at very low steam pressures, which was perhaps just as well in view of the nature of contemporary boilers. The production of engines which were light, compact, and altogether more economical was wholly dependent on the use of much higher working pressures. In the steamships of the 1820s, with steam pressures of about 10 psi, provided by square haystack * boilers, the coal consumption was around 15 pounds weight per horsepower hour. In the 1850s, engineers were still talking in terms of 20 psi and about 9 pounds per horsepower hour. By 1900, pressures had gone up to well over 200 psi, and coal consumption had fallen to 1 to 5 pounds per horsepower hour, a tenfold reduction in 80 years. It was not the steamship, as such, which drove sailing ships from the high seas, but the high-pressure steamship with triple expansion engines, Scotch boilers, low fuel costs and long range. The high-pressure boiler was not developed without incident. Throughout most of the 19th century, boiler explosions were relatively frequent and the consequences were sometimes very terrible. The American river steamers, in particular, were pioneers of high-pressure working. During the middle years of the century, the Mississippi steamboats used regularly to indulge in dramatic races over thousands of miles of river. The designers of these vessels were prepared to sacrifice almost everything to speed and lightness, and they took what might charitably be called an optimistic approach to boiler design. As a result, during the years 1859 to 60 alone, 27 of these ships were lost as a result of boiler explosions *. Although some of these accidents were due to criminal practices such as the tying down of safety valves, most of them were basically caused by lack of proper calculations. This was a pity because in fact the basic calculations needed to determine the stresses in simple pressure vessels are very easy. So easy indeed that, as far as I can find out, nobody has ever bothered to claim the credit for. As soon as we come to consider any kind of pressure vessel or container which includes such things as balloons and bladders and stomachs and pipes and boilers and arteries, we have to deal with tensile stresses which operate in more than one direction at the same time. This may possibly sound complicated but presents, in fact, no cause for alarm. The skin of any pressure vessel really performs two functions. It has to contain the fluid by being watertight or gas-tight, and it has also to carry the stresses set up by the internal pressure. Nearly always this skin or shell is subjected to tension stresses acting in both directions in its own plane, that is to say, parallel to its surface. The stress in the third direction, perpendicular to its surface, is usually negligibly low and can be forgotten about. It is convenient to look first at pressure vessels of spherical shape. The skin or shell of the bladder-like object in Figure 1 is supposed to be reasonably thin, say less than about 1/10 of the diameter. The radius of the shell, taken at the middle of the wall thickness, is r. The thickness of the wall or shell is L and the whole thing is subject to an internal fluid pressure of P, all these being in whatever units we happen to patronize. If we imagine that we slice the thing in two, like a grapefruit, then from figures 1, 2, and 3 it is pretty clear that the stress in the shell in all directions parallel to its own surface will be. This is a useful practical result, and it is in fact a standard engineering formula. Spherical containers have their uses, but clearly cylindrical vessels have wider applications, especially to things like pipes and tubes. The surface of a cylinder has no longer the same sort of symmetry as that of a sphere, and so we cannot assume that the stress along a cylinder is the same as that around its circumference, and in fact it isn't. Let us call the stress in the shell along the length of the cylinder S. X and that around the circumference of the shell S. 2. Figure 1. A spherical vessel with internal pressure P, mean radius r, and wall thickness T. Figure 2. Imagine the vessel sliced in two across any diameter. The resultant of all the pressure forces acting on the inside of each half of the shell must equal the sum of all the stresses which would have acted on the cut surface, whose area is 2 prt. Figure 3. The resultant of all the pressure forces acting on the inside curved surface of a hemisphere will be equal to the same pressure acting on a flat disk of the same diameter, which must be pr2p. Hence, from figure 4 we can see that the stress along the shell, S. 1 must be the same as that in the sphere which we have just been considering, that is to say, to get at S. 2, the circumferential stress in the shell of the cylinder, we now slice, in our imaginations, in the other plane, after the fashion of figure 5, from which we see that. Thus the circumferential stress in the wall of a cylindrical pressure vessel is twice the longitudinal stress, i.e. S. 2 equals 2s. 1, figure 6. One consequence of this must have been observed by everyone who has ever fried a sausage. When the filling inside the sausage swells and the skin bursts, the slit is almost always longitudinal. In other words, the skin has broken as a consequence of the circumferential, not the longitudinal, stress. Figure 4. The longitudinal stress, S. 1 in the shell of a cylindrical pressure vessel is the same as that in the equivalent spherical vessel. Figure 5. Circumferential stress in a cylinder, S. 2. These sums are continually cropping up in engineering and in biology. They are used to calculate the strength of pipes and boilers and balloons and air-supported roofs and rockets and spaceships. As we shall see in Chapter 8, the same simple piece of theory applies to the whole question of development from amoeba-like forms of life towards more elongated and mobile primitive creatures. Another consequence of the algebra we have just done is that to contain a given volume of fluid at a given pressure will require a greater weight of material if we use a cylindrical vessel than if we use a spherical one. Where weight is very important as it is with the oxygen bottles which climbers use at high altitudes and also with aircraft starter bottles, then spherical vessels are usual. For most other purposes, where weight is not so serious a matter, cylindrical bottles are cheaper and more convenient. The gas cylinders used in hospitals and garages are a case in point. There is an interesting problem which has to be solved by the designer of every sailing vessel. It is, what is the best method of preventing the ship from flinging her spars overboard? Opinion on this point is divided. There are two schools of thought, the Eastern and the Western schools. In the West we think the best way of keeping the masts in the ship is to fasten them rigidly in position with a complicated system of shrouds and stays. The disciples of the Eastern school hold that this is all nonsense besides being very expensive. They stand a tall and rickety mast on end, set upon it vast areas of gunny mats, bamboo matting or anything else that comes to hand, and then keep the whole business erect by the power of faith. At least, I have never been able to discover any other power interesting itself in the miracle. Weston Martyr, the South Seaman. The theory of pressure vessels, which we have just derived, also applies, with minor modifications, to things other than closed containers, that is, to open membranes and fabrics which have to sustain pressure from the free movement of wind or water. Of such a nature are tents and kites and awnings and fabric-covered aircraft and parachutes and the sails of ships and windmills and eardrums and fishes' fins and the wings of bats and pterodactyls and the sails of the jellyfish called Portuguese men of war. For all such purposes it is expedient and economical, as we shall see in Chapter 14, not to use a rigid panel or shell or monocoque but to cover a stiff open framework of rods or spars or bones with some kind of flexible fabric or skin or membrane. Such a structure cannot be quite rigid, and it will be realized that, as soon as any lateral force comes upon the membrane by reason of the pressure of wind or water, it must deflect or bow into a curved shape which, to a first approximation, may be treated as a part or segment of a sphere or cylinder, and so the stresses in the membrane will obey much the same laws as those in the shell of a pressure vessel. From this it is very easy to show that the force or tension in the membrane, per unit width, is PR, the product of the wind pressure, P, and the radius of curvature, R, of the membrane. Thus the more sharply the membrane is curved the less the force in it will be, and so the load which it puts upon the supporting framework will also be diminished. When the wind blows, the pressure caused by the wind increases as the square of the wind velocity. In a strong wind the pressure becomes very high indeed and so do the loads upon the supporting structure. According to our Western, engineering school, way of thinking there is very little we can do about this. For we would rather be seen dead than allow the membrane whether it be a sail or part of an aeroplane or whatever to bulge appreciably between its supports. Of course, we can never manage to keep the fabric perfectly flat, but we do everything we can to keep it as taut as possible. What we actually do is to make the supporting framework strong and heavy and expensive and hope that it won't break, which of course it often does. For instance, the rig which has been developed for modern racing yachts generally consists of tubular metal spars and almost inextensible terylene sails. This aerodynamic mechanism is kept up to a feeling of tenseness which is anything but restful. A simpler and cheaper way of doing the job is to arrange for the sail to bulge between its supports so that, as the wind pressure increases, the radius of curvature diminishes. And so the tension force in the canvas remains roughly constant however hard the winds may blow. Naturally, one has to ensure that the distortions which help to ease the structural problem do not create aerodynamic ones. Figure 7. Chinese junk rig. One elegant and satisfactory way of doing this has been devised by the Chinese, who, after all, have been sailing about the seas in moderate comfort and safety for a good many centuries. The rig of the traditional Chinese junk varies according to local custom but is generally very much like Figure 7. The battens which cross the sails are attached to the masts and, since the whole rig is constructed from flexible materials, as the wind increases, the sail bows out between the battens after the fashion of Figure 8 without much loss of aerodynamic efficiency. If it doesn't bulge enough it is quite simple to ease the halyard until it does. Lately, Colonel Blondie Hassler, of Bordeaux raid fame, has taken up the Chinese lug sail with very satisfactory results. Several yachts with Colonel Hassler's rig have made long ocean voyages with success and in a comparatively relaxed manner. They hang gliders which are now so popular are designed on much the same principles, and, although they may shock the traditionalists, they are cheap and strong and they do seem to work. Figure 8. Edge on view of a junk sail with halyard eased. Take from the goblin his crinkly face, his pointed ears from the gnome. Borrow the nose of a leprechaun and smuggle it carefully home. Sew balky fingers to banshee wrist. Stitch gossamer vellum between. Fit legs to straddle with knees a twist from a body of velveteen. Douglas English, Punchy, July 11, 1923. The resemblance between a bat and a Chinese junk is immediately obvious. Figure 9. In all bats the wings are constructed by stretching a membrane of very flexible skin over a framework of long, thin bones which are, in essence, the fingers of a hand. Fruit bats, for instance, are quite large animals with a wingspan of 4 feet or something over a meter. In their native India, where they are a pest, they think nothing of flying 30 or 40 miles in a night in order to rob an orchard. Since they can do this without becoming unduly exhausted they must therefore be efficient flying machines. Furthermore, to save weight, as well as what is called metabolic cost, they have gone a long way in the matter of cutting down the thickness of their wing bones. Figure 9. The fruit bat. When a fruit bat is photographed in flight it can be seen that, on the downstroke of the wing, the skin membrane bulges upwards into a form which is roughly semicircular, thereby minimizing the mechanical load upon its bones. It is clear that there can in practice be little or no aerodynamic loss as a consequence of this change of shape. About 30 million years ago the place of birds was largely filled by a wide range of flying. Figure 10. Pteranodon. Some of these animals were very large. Fossil remains of Pteranodon, for instance, have been recovered which show that this beast reached a wingspan of 8 meters, 27 feet, and possibly more. It stood about 3 meters high, 10 feet, and it seems that its total weight was probably only about 20 kilograms, 44 pounds. There was therefore little weight available either for bony structure or for flying muscles. Recently, the discovery of even larger pterodactyls, about twice the span of Pteranodon, has been reported from America. Pteranodon was probably pelagic, that is to say, it filled, roughly speaking, the ecological niche which is now occupied by the albatross. Like the albatross, it seems to have lived mostly in the air, soaring close above the deep-sea waves and fishing on the wing. Even more than the fruit bat, the wing bones of Pteranodon appear, from the fossils, to have been almost unbelievably thin and fragile. Of course, we know nothing experimentally about the elasticity of the skin which covered these vast wings, but it seems fair to infer that this skin must have behaved very much like that of a bat. The aerodynamic efficiency of the whole system must have been high and comparable to that of the modern albatross. Although bats flourish and survive very well today, pterodactyls were superseded by birds, which have feathers, a great many years ago. It is possible, of course, that the extinction of pterodactyls had nothing to do with structural considerations, but it is also possible that there is something special about feathers which gives birds an edge over other flying creatures. When I worked at the Royal Aircraft Establishment I used to ask my superiors, from time to time, whether it would not perhaps be better if aeroplanes had feathers. But I seldom succeeded in extracting a rational or even a patient answer to this question. But, after all, why do birds have feathers? Given the job of designing a flying animal, a modern engineer would perhaps produce something like a bat, or possibly some sort of flying insect. I do not think that it would occur to him to invent feathers. Yet presumably there are very good reasons for their existence. One imagines that both bats and pterodactyls tend to lose a good deal of energy in the form of heat from the skin of their wings, but then reasonable heat insulation could be provided by fur. Perhaps this is what did happen at an early stage in the evolution of birds, because feathers, like horns and claws, developed from hair. However, hair is presumably better when it is soft, and so the keratin from which hair is made has quite a low Young's modulus. In feathers the keratin molecule has been made stiffer by cross-linking the molecular chains with sulfur atoms, which accounts for the smell of burnt feathers. There are, no doubt, aerodynamic advantages in using feathers, since their employment extends the choice of outside shapes which the animal can make use of. For one thing, thick wing sections have often better aerodynamic efficiencies than the thin ones which result from membranes. It is easy to get an efficient thick section by padding out the wing profile with feathers at the cost of very little weight increase. Furthermore, feathers are better adapted than skin and bone for providing anti-stalling devices such as slots and flaps. However, I am inclined to think that the main advantage of feathers to an animal may be structural. Anybody who has flown model aeroplanes knows, to their cost, how vulnerable any small flying machine must be to accidental damage from things like trees and bushes, or even from careless handling. Many birds fly constantly in and out of trees and hedges and other obstacles. Indeed, they use such cover as a refuge from their enemies. For most birds the loss of a reasonable number of feathers is not a very serious matter. Besides, it is better to leave the cat with a mouthful of feathers than to be eaten. Feathers not only enable birds to get away with more local scrapes and abrasions than other animals, but the body of the bird is protected from more serious damage by its thick resilient armor. The Japanese feather armor which one sees in museums was not, as one might suppose, the picturesque nonsense of a primitive people who did not know any better. It was an effective protection against weapons like swords. In the same kind of way, during the Russo-Finnish War, Finnish armored trains were protected by bales of paper, and modern fighter pilots' splinter-proof boots are made from many layers of cellophane. When a hawk kills a bird in the air it does not usually do so by wounding it with its beak or talons which would probably not penetrate the feathers. It kills by have a high work of fracture. The work of fracture mechanism of feathers is something of a mystery. At the time of writing I do not think anybody knows how it works. Like so many work of fracture mechanisms, that of feathers is sensitive to what appear to be small changes. Everybody who has kept and flown hawks knows that these intelligent, exacting, and maddening birds LPSE condition very easily. Even when they are properly fed and exercised in captivity, hawks' feathers are very apt to become brittle and break off with undue frequency. The cure or palliative for this is to join the broken parts of the feather together again by imping star. This is done by inserting a double-ended imping needle, with a little glue, inside the hollow of the shaft at the break. The details of this process are described in the 16th century books on hawking. When one considers the appalling and expensive frequency with which motor cars nowadays incur bumps, bashes, and abrasions, one sometimes wonders whether they have not a lesson to learn from the birds. Incidentally, I am told that, since the American Army practically lives on chicken, there exist somewhere in the United States enormous quantities of unwanted chicken feathers. It would be rather nice to find a use for them. The muscular mechanism has recently been understood. It works by feeding energy into edge dislocations which operate, as it were, in reverse. For edge dislocations, see the New Science of Strong Materials, Chapter 4. The number of vibrations per second, i.e. the frequency, n, of a stretched string can be written. Where L equals length of string, P equals density of material from which string is made, kgm3. S equals tensile stress in string, n/m2. But then, during the same period, 83 steamboats were destroyed by fire, 88 by running into sunken trees, and 70 from other causes. It seems that life on the Mississippi, in the showboat days, was not uneventful. A partial solution was provided by Mariotta around 1680, but of course he was unable to make use of the concept of stress. Also about creep and chariot wheels. And here I want to tell you a story about a ship that was made during the war. She was a steamer, and she was built of good wood, and the men who designed her were good and able craftsmen too. She went along like a man who carries too heavy a burden, and presently she tripped and stumbled. It was only a little ground swell. And she opened out and fell apart like a flimsy old crate that someone had stepped on. In 5 minutes there was nothing there at all except a floating scum of coal dust, with some timbers and an odd man or two bobbing about in the middle of it. This is a true story, but the point I want you to notice is that this ship was made by carpenters, house carpenters, shore carpenters, and she was not built by shipwrights at all. Weston Martyr, the South Seaman. The steamer in Weston Martyr's story sank, rather suddenly, because the joints which were supposed to hold her timbers together were much too weak. Although the house carpenters who built her, who were honest men in their own way, were presumably satisfied with them. In fact, when a shore carpenter is building a house or putting together traditional furniture, he is in the habit of making joints which a naval architect or an engineer would regard as weak and highly inefficient. Weak these joints certainly are, whether they are inefficient depends upon what one is trying to do. The purposes of a builder of houses may not be at all the same as those of a builder of ships or aeroplanes. It is perhaps too often assumed by engineers that an efficient structure is always one in which each component and each joint is exactly strong enough for the loads which it has to bear, so that, for a given strength, the smallest amount of material is used and the weight is minimized. Such a structure would, ideally, be equally likely to break anywhere. Or indeed, like the one-hoss shay, it might break everywhere at once. To work towards this kind of efficiency calls for great vigilance on the part of the engineer, since the least fault in design or manufacture must introduce a dangerous weakness. Approximations to this kind of structure do, of course, exist, especially in ships and aeroplanes and in some kinds of machinery where weight saving is very important. However, this represents an unduly specialized way of looking at the problem of efficiency, and it takes no account of the need for rigidity, let alone of the need for economy. Structures of the one-hoss shay type are sometimes. Builders and joiners have more sense than to go in for fancy structures of this kind. Houses are quite expensive enough as it is. And these people know very well that in the great majority of the common or stationary affairs of life the design of a structure is influenced much more by its stiffness than by its strength. Indeed, it is the relative importance of the need for strength and for stiffness which really lies at the root of the question of the cost and efficiency of structures. Where the need is chiefly for rigidity rather than strength, the whole problem becomes very much easier and cheaper. This is nearly always the case with furniture and floors and staircases in buildings generally, and also with cookers and refrigerators and with many tools and heavy machinery and with some of the parts of motor cars. These things do not very often break, but, if we made the material much thinner, the deflections and bendiness and general wobbliness would soon become unacceptable. Thus, to be rigid enough, the various parts generally have to be so thick that the stresses in them are very low, often, from the engineer's point of view, absurdly so. It follows that, in structures of this kind, even if the material is riddled with defects and stress concentrations, it probably does not matter very much, and, what is more, the strength of the joints is unlikely to be critical, in many cases. A few nails may be perfectly adequate. This sort of thing is, of course, the basis of most people's instinctive approach to design. Millions of people who have never heard of Hooke's law or Young's modulus can guess the stiffness of a table or a chicken coop quite nearly enough by experience and common sense, and, if such things are made stiff enough, They are very unlikely to break under their ordinary, everyday loads. Furthermore, a little bit of give in some of the joints may be no disadvantage, and this is more likely to be available in a traditional joint than in a sophisticated one. For one thing, a certain amount of flexibility may enable the loads to be evened out in a beneficial way. Although it is true that furniture does not very often get broken, quite a good way of attempting to do so is to sit on a chair, 3 of whose legs are on the carpet while the 4th rests, hopefully, on the bare floor. With traditional furniture, the load may be spread over all the 4 legs by the distortion of the tenant joints. In modern factory-made chairs with efficient glued joints, these joints may just break, after which the chair is difficult to repair in any satisfactory way. Another reason for encouraging a certain amount of flexibility in joints is that wood, and sometimes other materials, change their dimensions with the weather. Wood shrinks and swells in the cross-grain direction by up to 5 or even 10%, or traditional joinery allows for this by means of inefficient slotted joints. In Churchill College we had a fine new high table made from the best and most expensive wood, which had been scientifically glued together with strong, rigid joints. After a few months in the scientifically heated hall, this table shrank and split down the middle. The result was not an unobtrusive little crack but a crevasse many yards long and quite capable of providing sheltered accommodation for large numbers of peas of normal or standard diameter. Many deflection-controlled peasant structures are wholly excellent in their proper places, but when we come to demand weight saving and strength and mobility we may get into all sorts of difficulties, especially in relation to the reliability of the joints between the various parts. Historically, this has always been the most serious problem in ship construction and in windmills and water mills. The great skill of the old shipwrights and millwrights lay in somehow combining sufficient strength for safety with the modicum of flexibility needed to allow for the working of timber. The older shipwrights erred on the side of flexibility, and, though their ships were often excessively leaky, they seldom actually broke at sea. It required the administrative abilities of modern wartime governments to produce wooden ships which really did fall to pieces. Troubles with joints in ships and aircraft were a fairly prominent feature of both the world wars. During the First War the Americans built a large number of wooden ships, both steam and sail, frequently by unorthodox methods, and many of these ships broke up. In the Second War they produced even greater numbers of welded steel steamers, of which an even higher proportion broke, either at sea or in harbor. In England, in both wars, we manufactured very large quantities of wooden aircraft, which always seemed to be having joint troubles of one kind or another. As far as aircraft are concerned this was not wholly surprising, for I remember being shown, right inside vital glued joints in the main structure, on various separate occasions. 1. A pair of scissors. 2. A first aid manual, pocket size. 3. No glue at all. On the whole I do not think that most of these accidents were caused by subnormal or abnormal people. I am afraid the guilt generally lay with very ordinary people, and that was just the trouble. Naturally, people get tired or bored, but I think the root of the matter was much deeper than that. Very few of those who made, or failed to make, these joints had any personal experience of a situation in which the failure of a joint could cause a fatal accident. Though collectively they had a great deal of experience of things like cupboards and garden sheds, where the strength of the joints really mattered very little. All our efforts to persuade them that a badly made joint was morally equivalent to manslaughter foundered on a deeply held folk tradition that it was silly to fuss about such things and that strength is a boring subject anyway. All this would not have mattered so much if it had not been practically impossible to inspect the joints properly after they were made. In more recent years very efficient metal-to-metal adhesives have been developed which have a number of solid technical advantages, always provided that the joints are really conscientiously made. Unfortunately, their use in modern aircraft has been handicapped by the fact that it has proved necessary to provide a separate inspector to watch each worker throughout the gluing operation. Also inspectors to inspect the inspectors. Rather naturally, these arrangements have proved expensive. In spite of all this, I am told that the use of glue in modern metal aircraft is increasing. Since the function of a joint is to transmit load from one element of a structure to its neighbor, stress has somehow got to get itself out of one piece of material and then get itself into the adjoining piece. Such a process is only too likely to result in severe concentrations of stress and consequent weakness. All the same, in a few favorable circumstances it may be possible to arrange for the stress to pass uniformly across the joint from one component to the other with little or no concentration of stress. This is more or less the case with a glued scarf joint in timber, Figure 1, and a butt weld in metal. Figure 2. Figure 1. Glued scarf joint in timber. Figure 2. Butt weld in metal. However, it is by no means always practicable to use scarfed or butt welded joints, and some form of lapped joint between two adjacent planks or plates is probably more common. This sort of geometry at once introduces stress concentrations, and as far as a rigid lapped joint is concerned it does not make much difference whether the joint is glued, nailed, screwed, welded, bolted or riveted. In all cases most of the load is transferred at the two ends of the joint. Figure 3. Figure 3. Load transfer in a lapped joint. For this reason the strength of such joints depends largely upon their width and very little upon the length of the overlap between the parts. This is why the simplest and commonest forms of riveted and welded joints between two metal plates, figures 4 and 5, are reasonably effective and not much improved by complicating them. Figure 4. Riveted lapped joint. Figure 5. Welded lapped joint. Very often we want to provide an end attachment for a tension bar or rod to some kind of socket or solid anchorage. Again much the same considerations apply, except that in this case there is only one stress concentration, which usually occurs at the point where the rod enters its socket. Figure 6. If the rod is screwed into its anchorage, for instance, nearly all of the load is taken out by the first 2 or 3 threads, and any extra length of rod within the socket will do little or no good. Thus the difficulty which a thrush has in pulling a worm out of a lawn does not depend on the length of the worm. A short worm is just as hard to extract as a long one. Figure 6. The distribution of stress which is shown in Figure 6 applies when the two components of the joint have similar Young's moduli, which is usually the case with metal-to-metal joints. It also applies when the rod or tension bar is less stiff than the material of its socket or anchorage, which appears to be the case with worms and lawns. If the rod or bar is substantially stiffer than the material into which one is trying to anchor it, however, the stress situation may be reversed and the stress concentration may exist mainly at the bottom or inner end of the rod or insert. Figure 7. In practice, of course, both situations are likely to weaken the joint about equally. There may exist, perhaps, a ratio between the modulus of the insert and that of its surroundings which would given wire cables with frayed out ends like the roots of a tree into the body of the plastic. When specimens of this ill-conceived construction were loaded in a testing machine, the wires pulled out of the plastic with a succession of cracking noises and at ridiculously low loads. Figure 7. Load transfer in embedded rods under tension. In the next experiment sword-like tapered steel blades or prongs were substituted for the cables and were molded into the plastic wing structure after being coated with a suitable adhesive. Figure 8. This time the test specimen failed, not with a series of cracking noises, but with one loud bang, but still at just as low a load. Figure 8. The wrong shape for a steel insert. This arrangement is weak. After a pause for reflection and intelligent thought about worms, we tried out a series of wide spade-shaped steel inserts which were much shorter and looked something like Figure 9. All these failed at far higher loads which were, in each case, proportional to the breadth of the spade. By developing this design we were able to take out loads in the region of 40 to 50 tons from plastic structures by means of quite a small steel fitting. Figure 9. The right shape for a steel insert. This is much stronger. Such joints depend entirely upon the adhesion between the metal and the plastic and must therefore be molded conscientiously and under suitable inspection. They must also be designed with care, because, in all such cases, adhesion between a metal and a non-metal will fail completely as soon as the metal reaches its yield point and ceases to behave elastically. Since the stresses in the metal are much higher than one might expect, it is generally necessary to make the insert from high tensile steel, carefully heat-treated. Furthermore, the trailing edge of the steel insert must be ground sharp, like a chisel. "I've got 1/fraction of an inch of play, at any rate," said the garboard Strake, triumphantly. So he had, and all the bottom of the ship felt easier for it. "Then we're no good," sobbed the bottom rivets. We were ordered never to give. And we've given, and the sea will come in, and we'll all go to the bottom together. First we're blamed for everything unpleasant, and now we haven't the consolation of having done our work. "Don't say I told you," whispered the steam, consolingly, "but, between you and me and the last cloud I came from, it was bound to happen sooner or later. You had to give a fraction, and you've given without knowing it. Now hold on, as before." Rudyard Kipling, The Ship That Found Herself. Riveted joints in steel structures are rather out of fashion, chiefly because they are expensive but partly because they tend to be heavier than welded joints. This is a pity, because riveted joints have several advantages. A riveted joint is reliable and easy to inspect, and in a large structure it acts to some extent as a crack stopper, that is to say, if a really large and healthy Griffith crack gets underway, it may quite often, though not infallibly, be stopped or delayed by the mote or discontinuity of a riveted joint. Even more importantly, riveted joints can slip a little and so redistribute the load, thus evading the consequences of the stress concentrations which are the bane of all joints. The process has been described for all time in The Ship That Found Herself, and indeed Kipling's feeling for the problems of stress concentrations and cracks in structures, many years before Inglis and Griffith, is very remarkable. Some of his stories about structures might well be required reading for engineering students. Because each individual rivet can slip very slightly, the worst effects of stress concentrations may be reduced, and so it may be worthwhile to make lap joints having several rivets in series. Since the end rivets may be able to slip enough to enable those in the middle to do some work. When a newly made riveted joint between steel or iron plates has settled itself into a reasonable distribution of load, then rust may have a chance to play its beneficent part. The products of corrosion, iron oxides and hydroxides, expand and so lock the joint and prevent it from sliding backwards and forwards when the load is reversed. Furthermore, the rust transmits some of the shearing forces between the plates, rather like a glue, and therefore the strength of a riveted lap joint generally increases with age. Figure 10. 3 of the ways in which a riveted joint may fail. A. Failure by shearing the rivets. B. Failure by tearing the rivets out of the plate, i.e. by bearing or elongation of the holes. C. Failure by tearing the plate. When rivet holes are made in large steel structures, such as ships and boilers, it is usual to punch them. Although this is a quick and cheap way of making holes in steel, it is not entirely satisfactory, since the metal at the edge of the hole is left in a brittle condition and also often contains small cracks. Since there will certainly be stress concentrations in this region, this is not a good state of affairs. For this reason, in high-class work, it is usual to punch the holes undersize and then ream them. Although it also adds materially to the strength and reliability of the joint. Both riveted and bolted joints can be made in all sorts of different shapes and sizes, but, broadly, doing a suitable calculation. However, rules for the design of riveted joints are laid down by organizations like Lloyd's and the Board of Trade, and these are to be found in nearly all the engineering handbooks. Welded joints of all kinds are very widely used in steel work today, mainly because welding is generally cheaper than riveting and also because there is some increase in strength and saving in weight. In ships, too, the absence of rivet heads below the waterline reduces the resistance by a small amount. Most sophisticated welding is electric arc welding. In this process the welder holds a metal rod, the welding rod, in his right hand by means of an insulated clamp. With his left hand he generally holds a mask or screen, furnished with very dark glass, through which he can safely watch the arc, which he strikes and holds between the tip of the rod and the seam which he is making. At the usual 30 to 50 volts the arc is perhaps a quarter of an inch, 7 millimeters, long and results in the transference of metal from the end of the welding rod to a little pool of molten steel which the welder coaxes along the joint. The result is, or should be, a continuous run or leg of weld metal, about a quarter of an inch, 7 millimeters, wide, which solidifies and bridges the joint. If a greater thickness of weld is needed, then the run must be repeated as many times as may be necessary. If the weld has been properly made it is generally very strong and satisfactory, but any lack of skill or attention on the part of the welder is likely to result in defects, such as slag inclusions, which weaken the joint and are not readily seen by an inspector. It is also easy for a clumsy welder to overheat enough of the surrounding metal to cause serious distortions. This is especially the case where the work to be welded is heavy and thick. The welded engine seatings in the pocket battleship Graf Spee, for instance, gave serious trouble from this cause. In theory a welded joint in a tank or a ship should be completely watertight without further treatment, but this is seldom the case. In practice welded construction is likely to give more trouble than riveted work in this respect. A riveted lap joint is easily caulked by spreading the edges of the plates by means of a pneumatic chisel or caulking tool. This cannot be done with a welded joint, and the best way of dealing with the situation is to inject some kind of liquid sealing compound under pressure into the space between the two welds of a lap joint. All the same, I remember seeing much trouble in connection with the water testing of compartments in welded warships. Once upon a time I had the privilege of working for a few weeks as a riveter and also as a welder in one of the Royal Dockyards, and during this time I learnt various things which I do not think are in the textbooks. Although closing a 2-inch rivet in an armored deck with a pneumatic hammer is both hard and noisy work, it is also curiously interesting. And most forms of riveting seem to me to have at least some of the attraction of golf with the advantage of being more useful. A further sporting element was added by the operation of the inspection process. In those days we were paid at the rate of so much for every rivet closed. But 5 times so much was deducted for every rivet which was condemned by the inspector and had to be drilled out and replaced. Riveting may not be heaven, but, by contrast, welding was certainly hell. Welding is amusing enough for the first hour or two, as I dare say hell may very possibly be, but after this the task of watching a hissing, flickering arc and a wretched little pool of molten metal becomes intolerably dull. And the dullness is not much relieved by the sparks and blobs of molten metal which find their way down one's neck and into one's shoes. After a very few days a feeling of boredom and bloody generally turns out to be very imperfect. Furthermore, a welded joint provides little or no barrier to crack propagation, and this is one reason why so many large steel structures have failed catastrophically in recent years. Homer knew that the first thing to do on getting your chariot out was to put the wheels on. John Chadwick, The Decipherment of Linear B, Cambridge University Press, 1968. The chariots of Mycenaean and archaic Greece had very light and flexible wheels, made from thin bent wood, willow or elm or cypress, usually with only 4 spokes, figure 11. Such a construction was highly springy and resilient, and it seems to have enabled these vehicles to be galloped across the rough ground of the Greek hillsides, where a heavier and more rigid vehicle would have been useless. In fact, the rim of the wheel bent, rather like a bow, under the weight of the chariot, and, just as a bow must not be left strung for any length of time, so the weight must not be left on the wheels of a chariot. In the evening, therefore, one either tipped the vehicle vertically against a wall with the weight off the wheels, as Telemachus did in Book 4 of the Odyssey, or else one took the wheels off altogether. Even on Mount Olympus the goddess Hebe had the morning chore of fitting the wheels to the chariot of grey-eyed Athene. With the much heavier wheels of later times such a procedure is less necessary and less practicable, although I understand that the wheels of the present Lord Mayor's coach are distinctly eccentric. Presumably because the weight has been left on them for long periods. Figure 11. The Homeric chariot wheel was essentially flexible and made by bending quite thin wood. It could easily distort or creep under any prolonged load. The distortion of bows and chariot wheels under prolonged loading is due to what the engineer calls creep. In elementary Hookean elasticity we assume, for simplicity, that if a material will sustain a stress at all, it will sustain it indefinitely, and also that the strains in a solid do not change with time, so long as the stress remains constant. In real materials neither of these assumptions is baggy. It is, however, much more pronounced in natural fibers, such as wool and cotton, than it is with the newer artificial fibers. This is why terylene sails not only keep their shape but do not need to be carefully stretched when new, as had to be done with cotton and flax sails. Figure 12. Typical time creep curves for a material subjected to a series of constant stresses, S, L, S, 2, S, etc. Creep in metals is generally less pronounced than it is in non-metals, and, although steel creeps significantly at high stresses and when heated, the effect can often be neglected when one is dealing with light loads at ordinary temperatures. Creep in any material causes the stress to be redistributed in a manner which is often beneficial, since the more highly stressed parts creep the most. This is why old shoes are more comfortable than new ones. Thus the strength of a joint may improve with age if the stress concentrations are diminished. Naturally, if the load on the joint is reversed, creep may have the opposite effect and the joint may be weakened. The effect of the distortions caused by creep is particularly conspicuous in old wooden structures. In buildings the roof often sags in a picturesque way, and old wooden ships are generally hogged. The ends of the ship droop while the middle part rises. This is very noticeable in the gun decks of HMS Victory. With metals such as steel we generally notice the effects of creep when the springs of a car sit down and have to be replaced. Although the amount of creep which is likely to occur varies greatly between different solids, the general pattern of behavior is very much the same for nearly all materials. If we plot deformation or 3. time but will also gradually progress to actual fracture and destruction, an effect we generally wish to avoid. Soils, too, creep under load like other materials, and thus, unless we build upon rock or very hard ground, we need to watch the settlement of foundations, which will usually need to be deeper for large buildings than for small. This is the reason for constructing large buildings on concrete rafts. Note the subsidence of the foundations of the arches of Clare Bridge in Plate 7. Note that, if an undrawn nylon thread be cast into a block of rigid plastic, the thread can always be drawn out of the plastic by pulling on it, however long the thread may be. This is a good way of making long and complicated holes, for instance in wind tunnel models, for pressure measurements. This is also true for the adhesion between metals and paint or enamel, including vitreous enamel, i.e. glass. Before the days of modern extensometers, engineers used to judge the yield point of hot-rolled steel by the load at which the mill scale, or black oxide film, cracked off the surface. This sort of thing is at the root of most of the stories about V.I.P.S being seasick when riding in state coaches. Or how to design a worm. I'm very glad, said Pooh happily, that I thought of giving you a useful pot to put things in. I'm very glad, said Piglet happily, that I thought of giving you something to put in a useful pot. A. Milne, Winnie the Pooh. When nature invented something called life, she may have looked around, a little anxiously, for a useful pot to put it in, for life would not have prospered for long naked and unconfined. At the time this planet presumably afforded rocks and sand, water, and an atmosphere of sorts, but it must have been rather short of suitable materials for containers. Hard shells could be made from minerals, but the advantages of a soft skin, particularly in the earlier stages of evolution, seem to be overwhelming. Physiologically, cell walls and other living membranes may need to have a rather closely controlled permeability to certain molecules but not to others. Mechanically, the function of these membranes is often that of a rather flexible bag. They generally need to be able to resist tension forces and to be able to stretch very considerably without bursting or tearing. Also, in most cases, skins and membranes have to be able to recover their original lengths of their own accord when the force which has been extending them is removed. The strains to which present-day living membranes can be extended safely and repeatedly varies a good deal but may typically lie between 50 and 100%. The safe strain under working conditions for ordinary engineering materials is generally less than 0 to 1%. And so we might say that biological tissues need to work elastically at strains which are about 1,000 times higher than those which ordinary technological solids can put up with. Not only does this enormous increase in the range of strain upset a number of the conventional engineers' preconceived ideas about elasticity and structures. It is also clear that strains of this magnitude cannot be furnished by solids of the crystalline or glassy type based on minerals or metals or other hard substances. It is therefore tempting, at least to the materials scientist, to suppose that living cells might have begun as droplets enclosed by the forces of surface tension. We must be quite clear, however, that it is very far from certain that this is what actually happened. What really did occur may have been something quite different or at any rate considerably more complicated. What is certain is that some features of the elasticity of animal soft tissues resemble the behavior of liquid surfaces and thus may possibly derive from them. If we extend the surface of a liquid, so that it presents a larger area than before, we shall have to increase the number of molecules present at the surface. These extra molecules can only come from within the interior of the liquid and they will have to be dragged from the inside of the liquid to its surface against the forces which tend to keep them in the interior, which can be shown to be quite large. For this reason the creation of a new surface requires energy, and the surface also contains a tension which is a perfectly real force. This is most easily seen in a drop of water or mercury, where the tension in the surface pulls the drop into a more or less spherical shape against the force of gravity. When a drop hangs from the mouth of a tap, the weight of the water in the drop is being sustained by the tension in its surface. This phenomenon is the subject of a simple school experiment where one measures the surface tension of water and other liquids by counting the drops and weighing them. Although the tension in a liquid surface is just as real as the tension in a piece of string, or any other solid, it differs from an elastic or Hookean tension in at least 3 important respects. 1. The tension force does not depend upon the strain or extension but is constant however far the surface is stretched. 2. Unlike a solid, the surface of a liquid can be extended, virtually indefinitely into as large a strain as one cares to call for, without breaking. 3. The tension force does not depend upon the cross-sectional area but only upon the width of the surface. The surface tension is just the same in a deep or thick liquid as it is in a shallow or thin one. Drops of liquid in air are of little use for biological purposes, because they soon fall to the ground. But droplets of one liquid floating within another liquid can continue to exist indefinitely and are of great importance both in biology and in technology. Systems of this kind are called emulsions and are familiar in milk, in lubricants, and in many kinds of paint. Droplets are generally spherical and the volume of a sphere is as the cube of its radius, whereas the surface area of a sphere is as the square of the radius. Thus, if 2 similar droplets were to join up so as to make one droplet of twice the volume, there would be a considerable net reduction in surface area and so in surface energy. So there is an energy incentive for the drops in an emulsion to coalesce and for the system to segregate into 2 continuous liquids. If we want the droplets to remain separate and not to coalesce, we have to arrange for them to repel each other. This is called stabilizing the emulsion and is rather a complex process. One factor in stabilization is the provision of a suitable electrical charge on the surface of the drops, which is why emulsions are affected by electrolytes such as acids and alkalis. If stabilization has been done small and round, there is a good deal to be said for surface tension as a skin or membrane or container. For one thing, such a skin is very extensible and it is also self-healing. For another, the problem of reproduction is greatly simplified, since, if a droplet swells, it can break into two and become two droplets. As far as I know, no present-day cell wall operates simply by a straightforward surface tension mechanism, but many of them do behave in a way which is mechanically rather similar. One of the difficulties about simple surface tension is that the tension force is constant and cannot be increased by making the skin thicker. This limits the size of any container made in this way. However, nature is quite capable of producing a material which will have the characteristics of surface tension right through its thickness, so to speak. A slightly embarrassing example may be familiar to many people. When the dentist tells one to spit into his basin, the resulting string or cord of saliva sometimes appears to be infinitely extensible and virtually unbreakable. What molecular mechanism is taking place is not at all clear, but the behavior of such a material in terms of stress and strain is very much as in Figure 1. Figure 1. Stress-strain diagram for steel, bone, and spit. Most animal tissues are not as extensible as spit, but a very high proportion of them do show rather similar characteristics up to strains of 50% or more. The urinary bladder in young people will stretch, more or less in this fashion, to around 100% strain, and that of dogs to about 200%. As we mentioned in Chapter 3, my colleague Dr. Julian Vincent has recently shown that, whereas the soft cuticle of male locusts and of virgin female locusts is content with a strain of something under 100%, that of the pregnant female will stretch to an incredible 1200%, and still recover completely. Although the stress-strain curve for most membranes and other soft tissues is not strictly horizontal, it is often very nearly so, at any rate up to the first 50% or so of strain. And we may well consider what the consequences of this sort of elasticity are. In fact, any structure made from such a material must necessarily resemble one made from films of liquid under surface tension, and in the froth on beer. If one should want to make an elongated animal from membranes of this sort, then the best thing to do seems to be to make it of a segmented construction, like Figure 2, and in fact this sort of thing is very common in worm-like creatures. Figure 2. A segmented animal. Stresses are equal in both directions in the surface. However successful this device may be for the cuticle of worms, it is of no use if what is wanted is a pipe or a tube, such as a blood vessel. For pipes, as we saw in Chapter 6, the circumferential stress is ineluctably twice the axial stress, and this differential is just what a membrane of the sort we have been discussing cannot furnish. So it is necessary to have a material whose stress-strain curve slopes upwards after the fashion of Figure 3. Figure 3. To make the skin of a cylindrical container, the stress-strain curve of the membrane must slope upwards so as to afford a circumferential stress which is twice the longitudinal stress. The most obvious kind of highly extensible solid which fulfills this condition is rubber, and there is nowadays a wide range of rubber-like materials available, both natural and artificial. Some of these solids will extend to about 800% strain. They are known to materials scientists as elastomers. We use rubber tubes for all sorts of technological purposes, and one might suppose that the obvious thing for nature to do would be to evolve a rubbery solid suitable for making veins and arteries. However, this is just what nature has not done and, as it turns out, for a very good reason. Become unstable, and the tube will bulge out. Like a snake which has eaten a football, into a spherical protrusion which a doctor would describe as an aneurysm star. Since one can easily produce this result experimentally by blowing up an ordinary child's cylindrical rubber balloon, Plate 3, my mathematics are probably right. Figure 4. Stress-strain curve for typical rubber. Since veins and arteries do, in fact, generally operate at strains around 50%, and since American Samoa any doctor will tell you, one of the conditions it is most desirable to avoid in blood vessels is the production of aneurysms. Any sort of rubbery elasticity is quite unsuitable for most of our internal membranes, and in fact it is comparatively rare in animal tissues. When we do the mathematics, it turns out that the only sort of elasticity which is completely stable under fluid pressures at high strains is that which is represented by Figure 5. With minor variations, this shape of stress-strain curve is very common indeed for animal tissue and particularly for membranes. You can feel that this is so if you pull on the lobe of your ear. It will be noticed that Figure 5 seems to beg the question of whether the stress-strain curve for such materials really passes through the origin, the point of zero stress and strain, or whether there is still a finite tension in the material when there is no strain, a state of affairs which is no doubt calculated to shock the souls of engineers brought up on Hookean materials like steel. As far as one can see, however, in the living body there seems to be nothing really corresponding to an origin. That is, there is, apparently, no real position of zero stress and strain, as there would be in any structure made from, say, soap films. The arteries, at any rate, are permanently in tension within the body, and, if they are dissected out of a living or a freshly dead animal, they will shorten fairly noticeably. As we shall see in the next section, this tension is perhaps an additional device to counteract any tendency of the artery to alter in length as the blood pressure changes. Or else it may represent a belated attempt to equalize the longitudinal and circumferential stresses within the artery wall, in other words an attempt to get back to the conditions of surface tension which may have existed in the dim past. When people are subjected to severe and prolonged vibration, for instance in the case of foresters using chainsaws, this tension may be lost and the arteries elongate and take up a meandering, convoluted or zigzag path. The heart is, in effect, a reciprocating pump which discharges blood into the arteries in a series of fairly sharp pulses. The work of the heart is eased, and the general well-being of the body is served, by the fact that, on the pumping or systolic part of the cardiac cycle, much of the excess of high-pressure blood is accommodated by the elastic expansion of the aorta and of the larger arteries. This has the effect of smoothing the fluctuations in pressure and generally facilitating the circulation of the blood. In fact, the elasticity of the arteries does much the same job as the air bottle affair which engineer often attach to mechanical reciprocating pumps. In this simple device, the surge of pressure which accompanies the discharge stroke of the pump piston is smoothed out by arranging for the liquid which is being pumped temporarily to compress a supply of air which is trapped in a suitable bulb or container. When the valve of the pump shuts at the end of its stroke, as that of the heart does in diastole, the liquid continues to be driven on its way by the recovery and expansion of the trapped air. Figure 6. Figure 6. The elastic expansion of the aorta and the arteries performs the same function in smoothing the fluctuations of blood pressure as does the air chamber attached to an engineer's reciprocating pump. This rhythmic expansion and relaxation of the artery is necessary and beneficial, and in fact, if the artery walls stiffen and harden with age, the blood pressure is likely to rise and the heart has to do container are made of. Therefore, if Hooke's law were directly and crudely obeyed, the longitudinal strain would also be half the circumferential strain, and the total extensions would be in due proportion, taking the dimensions into account. Now a major artery such as those which supply blood to our legs might be something like a centimeter in diameter and perhaps a meter long, if the strains were really in the ratio of 2 to 1. A simple calculation shows that a change of diameter of half a millimeter which is easily accommodated within the body would be associated with a total change of length in the artery of about 25 millimeters or about an inch. It is obvious that a change of length of this magnitude, occurring 70 times a minute, cannot and does not take place. If this sort of thing really happened, our bodies just would not work. To take an extreme case, one has only to imagine such a thing happening in the blood vessels which serve the brain. Fortunately, in real life, the lengthwise strains and extensions in pressurized tubes of all sorts and kinds are very much less than one might have anticipated or feared from this rather too simple argument. That this is so is due to something called Poisson's ratio. If you stretch a rubber band, it gets very noticeably thinner, and much the same thing happens with all solids, although with most materials the effect is less conspicuous. Contrariwise, if you shorten a material by compressing it, it will bulge out sideways. Both of these are elastic effects and they disappear when the loads are taken off. The reason why we do not notice these lateral movements in things like steel and bone is that both the longitudinal and the transverse strains are so small, but the effects are there all the same. The fact that this happens in all solids and that such behavior is significant in practical elasticity was first observed by the Frenchman S. D. Poisson, 1781–1840. Although he was born into rather dramatic poverty and got very little formal education before he was 15, Poisson was made an academician. One of the highest honors France has to offer at the age of 31 for his work on elasticity. As we said in Chapter 3, Hooke's law says that. Thus, if we apply a tensile stress, S. 1, to a flat plate, the material will be elongated or stretched elastically so that there will be a tensile strain in the direction in which we are pulling of. However, the material will also be contracted sideways, i.e. at right angles to S. 1, by some other strain which we may call E. 2. Poisson found that, for any given material, the ratio of E. 2 to E. 1 is constant, and this ratio is what we now call Poisson's ratio. We shall use the symbol Q in this book. Thus, for a given material subject to a simple uniaxial tension stress S. 1. Figure 7. When a solid is stretched by a tensile stress S. 1, it extends in the direction of S. 1 by a primary strain E. L, but it also contracts laterally by a secondary strain E. 2. From what we have just been saying. And since E. 1 equals S. 1/E, which is Hooke's law. Then. Value than 1/2, otherwise various naughty and inadmissible things would happen. This is only partly true, and the values for some biological materials can sometimes be very high indeed, often well over unity. Asterisk the experimental value for the Poisson's ratio for my tummy, measured recently by me in my bath, is about 1-0, see the footnote on p162. Thus, as we have said, the effect of Poisson's ratio is that, if we pull upon a piece of material, such as a membrane or an artery wall, in one direction it will get longer in that direction, but it will contract, or get shorter, in the direction at right angles. So if two tensions are applied, at right angles to each other, the effects will be additive and the strains will be less than we should expect if either of the stresses were applied separately. For two simultaneous stresses, S1 and S2, the total strain in the direction of S1 will be, and the total strain in the direction of S2 will be. Harking back to Chapter 6, the consequence of the existence of Poisson's ratio is that the longitudinal or lengthwise strain in the wall of a tubular pressure vessel which obeys Hooke's law is, where R equals radius, P equals pressure, and T equals wall thickness. It follows that the longitudinal elastic extension of a tube is much less than one might expect. For a Hookean material with a Poisson's ratio of I there will be no movement at all. In fact, as we have seen, the artery walls do not obey Hooke's law, and it is also probable that their Poisson's ratio is higher than I. Possibly these two effects offset each other, because experimentally very little lengthwise movement is observed. Asterisk no doubt the fact that arteries are permanently stretched within the body is a precaution against any residual longitudinal strain. The effects of Poisson's ratio are probably of very great importance in animal tissues, but they are also significant in engineering and the matter is continually cropping up in all sorts of connections. It should perhaps be added that, whereas the aorta and the principal arteries expand and contract elastically with each beat of the heart, in the manner we have just been discussing, the state of affairs with the smaller arteries is usually rather different. The walls of these lesser vessels are provided with muscular tissue which can increase their effective stiffness and so, by restricting the diameter, is able. Animals quite often break their bones and they sometimes tear their tendons, neither of which have the sort of elasticity we have been discussing, but it is very noticeable that the mechanical fracture of soft tissue seems to be rare. There are several reasons for this. Being so soft, skin and flesh can sometimes evade the effects of a blow by deflecting and escape with a bruise. The question of stress concentrations, however, seems to be more interesting, since the majority of soft animal tissues appear to be almost immune from this major cause of engineering catastrophes. For this reason the need for a factor of safety is much reduced, and thus the structural efficiency, that is, the load which the structure carries in proportion to its weight, may be quite high. This immunity is not just a matter of being soft and having a low Young's modulus. Rubber is indeed soft and has quite a low modulus, yet many of us can remember, as children, having taken our blown-up rubber balloons out into the garden where they very soon burst with a bang on encountering the prickles of the first rose bush. As children, we did not realize that, owing to the stress concentration and to the 10W work of fracture of rubber, a crack spreads very rapidly front a pinhole in stretched rubber. And it is rather doubtful if our tears would have been much abated if we had. However, the membrane of a bat's wing, for example, although it is much stretched in flight, does not seem to behave in this way. If the wing does get punctured, the tear seldom spreads and the injury soon heals, although the bat may be using its wings continually. The explanation lies, I think, in the very different elasticities and works of fracture of rubber and of animal membranes. There are at present virtually no data available about the works of fracture of biological soft tissues, but the shapes of the stress-strain curves are in most cases pretty well known. And this latter factor does seem to have a big influence upon the probability of fracture. The shell membrane of an egg seems to afford an interesting example. This is the membrane which you encounter at breakfast, just inside the shell of your boiled egg. It is one of the few biological membranes which obey Hooke's law, in this case up to its breaking strain of about 24%. A simple but slightly messy experiment with a raw egg will show that egg membranes tear very easily. This is, of course, what they are there for, since the first thing the chick has to do is to get out of its egg, which it does by pecking with its beak. Incidentally, the egg shell itself, with its rounded domed shape, is difficult to break from the outside but easy to break from inside. Egg membranes are rather exceptional, in that they exist in order to be broken after they have served their purpose of conserving the moisture in the egg and keeping out infection. As we have said, they possess a special sort of elasticity. Very possibly for this reason. However, the great majority of soft tissues have an elasticity which is quite different and is very much like Figure 5. Functionally, most of these tissues need to be tough. Although all the scientific reasons are not perfectly clear, it does seem that, Pragmatically, materials with this type of stress-strain curve are extremely difficult to tear. One reason is, perhaps, that the strain energy stored under such a curve and therefore available to propagate fracture, Chapter 5, is minimized asterisk. As we have said, a very high proportion of animal tissues behave, elastically, much in the manner of Figure 5. One must confess that, when this information first dawned on me, it seemed to me to indicate an eccentricity or quirk on the part of nature, who, poor thing, did not know any better, not having represents a really essential condition for the evolution and continued existence of the higher forms of life. Biologists, please note. Perhaps partly for these reasons the molecular structure of animal tissue does not often resemble that of rubber or artificial plastics. Most of these natural materials are highly complex, and in many cases they are of a composite nature, with at least two components, that is to say, they have a continuous phase or matrix which is reinforced by means of strong fibers or filaments of another substance. In a good many animals this continuous phase or matrix contains a material called elastin, which has a very low modulus and a stress-strain curve something like Figure 8. In other words, elastin is only about one stage removed, elastically, from a surface tension material. The elastin is, however, reinforced by an arrangement of bent and zigzagged fibers of collagen, plate 4, a protein, very much the same as tendon, which has a high modulus and a nearly Hookean behavior. Because the reinforcing fibers are so much convoluted, when the material is in its resting or low strain condition they contribute very little to its resistance to extension, and the initial elastic behavior is pretty well that of the elastin. However, as the composite tissue stretches the collagen fibers begin to come taut. Thus in the extended state the modulus of the material is that of the collagen, which more or less accounts for Figure 5. Figure 8. Approximate stress-strain curves for elastin and collagen. The role of the collagen fibers is not merely to stiffen the tissue at high strains, they also seem to contribute very much to its toughness. When living tissue is cut, either accidentally or surgically, in the first stage of the healing process the collagen fibers are reabsorbed and disappear, temporarily, for a considerable distance around the wound. It is only after the gap has been filled and bridged by elastin that the collagen fibers are reformed and the full strength of the tissue is restored. This process may take up to 3 or 4 weeks, and in the meantime the flesh around the wound has an almost negligibly low work of fracture. It is for this reason that, if a surgical wound has to be. Figure 9. Hypothetical morphology of elastin. A. Resting or unextended state. Chain molecules folded or mainly folded within droplets. B. Extended state. Chain molecules pulled out of droplets. Collagen exists in various forms, but it may consist of twisted strings or ropes of protein molecules, and its resistance to extension is basically due to the need to stretch the bonds between the atoms in the molecules, that is to say, it is a Hookean material much like nylon or steel. Why then does elastin behave as it does, almost like surface tension? The short answer is that nobody really knows, but Professors Weisfach and Anderson have suggested that this behavior may in fact be due to a modified form of surface tension. According to this hypothesis, elastin may consist of a network of flexible long-chain molecules operating within an emulsion. Since the molecules of the network are wetted by the droplets but not by the substance between them, it is energetically preferable for most of the length of these molecules to remain coiled or folded up within the drops. Figure 9a. Under tension, they are dragged out of the drops and extended. Figure 9b. Much of our body consists, of course, of muscle, which is an active substance capable of contracting so as to produce the tensions which are needed in the tendons and elsewhere. Muscle, however, contains collagen fibers, which can only play a passive part elastically. When dead muscle is stretched it has a stress-strain curve which is, again, very much like Figure 5, and it seems possible that the function of the collagen in muscle is to limit the extension of the muscle when it is in its relaxed or extended state. In other words, it acts as a sort of safety stop. As we have said, another purpose of collagen fibers in flesh is to put up the work of fracture. This is a good thing for the animal, but it is inconvenient for the people who want to eat its flesh. In other collagen fibers into gelatin, which is jelly or glue, by roasting or frying or boiling. It is science of this kind which restores one's faith in the beneficence of Providence. Asterisk. The mechanical problem is often much complicated by the association of muscle tissue and other active devices for contraction, but we shall ignore this for the present. Asterisk. The theory of surface tension was originally worked out, independently by Weyong and by Laplace, about 1805. Asterisk. Since in all such cases, E2 is always of opposite sign to E. UQ or Poisson's ratio ought always to be negative, and it should therefore carry a minus sign about with it. However, we choose to forget about this and omit the minus sign. This is compensated for by putting a minus sign in the sums, such as those we are now doing. Asterisk to save indignant Elastikians from the trouble of unnecessary correspondence, I do know about the energy changes involved. These anomalies have a rational explanation. Asterisk note for bioelastikians. This Hookean analysis is simplistic. For a non-Hookean system, where the tangent moduli are E1 and E2, then, approximately, the change of longitudinal strain is 0 when. Although most soft tissues preserve approximately constant volume, that is, they seem to have a true Poisson's ratio around 0. 5. Most membranes choose to deform in plane strain, that is to say, they do not get thinner when they are stretched, and so they show an apparent Poisson's ratio of about 1 to 0. Like my tummy. This fits with a value of E1/E2 of around 2 to 0, which is likely enough. But why does the membrane not get thinner when it is strained? See, for instance, E. A. Evans, PROCINTCONF on Comparative Physiology, 1974, North Holland Publishing Company. Asterisk the shape of the stress-strain curve for most animal tissues such as skin is very much like that of a knitted fabric, which it is almost impossible to tear. Asterisk since this was written, Dr. J. M. Gosline has put forward an alternative hypothesis to account for the behavior of elastin.